Imagine a time when there was no time, no space, no matter. This was the state of the universe before the Big Bang. Then, in a fraction of a second, everything changed. The universe exploded into existence in an event we call the Big Bang. It wasn't an explosion in the traditional sense, like a firework going off in the sky. Instead, it was the rapid expansion of space itself. Imagine a tiny dot suddenly inflating to become a vast cosmos. This expansion continues even today. In the first moments after the Big Bang, the universe was incredibly hot and dense. It was like a cosmic soup of energy and elementary particles. But as the universe expanded, it cooled. This cooling allowed for the formation of the building blocks of matter. The Big Bang is the foundation of our understanding of the universe. It explains why distant galaxies are moving away from us. It also explains the cosmic microwave background radiation, a faint afterglow of the Big Bang that we can still detect today. In the early universe, energy reigned supreme, but as the universe cooled, this energy began to condense into matter. This process is described by Einstein's famous equation, E equals mc squared, which tells us that energy and matter are interchangeable. The first particles to form were quarks and leptons, the most fundamental building blocks of matter. Quarks would later combine to form protons and neutrons, the particles found in the nucleus of an atom. Leptons include electrons, which orbit the nucleus. The early universe was a chaotic place. Particles collided at incredible speeds, constantly being created and destroyed. But as the universe continued to cool, these collisions became less energetic. This cooling allowed for the formation of stable atoms, the building blocks of everything we see around us. The universe was finally ready to transition from a sea of particles to a cosmos filled with stars and galaxies. As the universe expanded and cooled, gravity began to exert its influence. Gravity pulled matter together into clumps, some larger than others. These clumps of matter continued to grow, attracting more and more gas and dust. Eventually, these massive clouds of gas and dust became so dense and hot that nuclear fusion began in their cores. Hydrogen atoms, the simplest and most abundant element in the universe, were fused together to form helium, releasing enormous amounts of energy in the process. These were the first stars, massive and luminous, illuminating the darkness of the early universe. They were very different from the stars we see today. They were much larger and hotter, and they lived much shorter lives. These early stars played a crucial role in the evolution of the universe. They produced the first heavy elements like carbon, oxygen, and iron in their cores. When these stars eventually exploded as supernovae, they scattered these elements throughout space. While stars were igniting across the universe, gravity continued to shape the cosmos on a grander scale. It drew the early stars together into vast collections that we call galaxies. Imagine a swirling cloud of gas and dust, much larger than any single star. Within this cloud, gravity pulled matter together, forming stars and clusters of stars. Over billions of years, this chaotic cloud gradually transformed into a structured galaxy. Our own galaxy, the Milky Way, is a barred spiral galaxy, a vast collection of billions of stars arranged in a flattened disk with spiral arms. The Sun, our very own star, resides in one of these spiral arms, about two-thirds of the way out from the galactic center. Galaxies are not randomly scattered throughout the universe. They are connected in a vast cosmic web, with clusters of galaxies forming at the intersections of this web. This structure provides clues about the distribution of matter in the early universe.